Welcome to the Explainer, specifically tailored for our digital signal processing lab. Today, we are absolutely bridging the gap between heavy, sometimes intimidating DSP theory and actual, practical Python code. We're going to do this by exploring infinite impulse response, or IIR filters. Now, you might be wondering, why do we care about IIR filters? Well, whether you're building digital audio effects to process acoustic signals, or maybe filtering highly sensitive biomedical signals like ECG sensor data, or even just trying to clean up RF communications, understanding how to effectively filter out noise is absolutely critical. It's a foundational skill. So we're going to take this entire process from the raw mathematical concepts right down into the trenches with the code, all the way to generating beautiful, functional plots using Python. Let's get started.
Here is a quick look at our agenda for today. First, an intro to IIR filters. Second, we'll look at the FIR versus IIR trade-offs. Third, we're covering the pole zero method. Fourth, the bilinear transformation technique. And finally, number 5, we'll bring it all together with Python code and plots.
All right, section 1. Let's jump right into the introduction to IIR filters.
Okay, so if we look at the definition, the absolutely crucial point is right here. Recursion. This is the heart of an IIR filter. Because an IIR filter is recursive, it actually feeds previously calculated outputs right back into the current calculation alongside your current and past inputs. It's like a feedback loop in a sound system. Mathematically speaking, because of this constant feedback loop, the filter's impulse response never completely dies out. It just gets infinitely smaller but never truly hits zero. It literally runs back on itself continuously. And that exact feedback mechanism is the defining characteristic that gives the infinite impulse response filter its name.
Moving on to section 2, let's talk about the FIR versus IIR trade-offs.
So, a really common question is, if IIR filters are infinitely recursive and rely on this feedback loop, why do we even use them instead of standard finite impulse response, or FIR filters? Well, it all comes down to the classic engineering trade-off. Think of it kind of like choosing between a high-performance sports car and an ultra-efficient hybrid vehicle. FIR filters, they give you perfect signal timing. We call this linear phase. Linear phase means that every single frequency in your signal is delayed by the exact same amount of time as it passes through the filter, which completely prevents any distortion of the signal's actual physical shape. That is an absolute must-have for things like high-speed data transmission where the shape of the wave is the data. But that perfection, it comes at a massive computational cost. IIR filters, on the other hand, offer extreme, almost unbelievable efficiency. They can meet super strict design specifications using a fraction of the computational steps and very minimal coefficients. But the cost for that speed is that they sacrifice that perfect linear phase, meaning different frequencies might be delayed by slightly different amounts, lightly warping the signal shape. Ultimately, if your project prioritizes minimizing processing power and maximizing real-time speed over absolutely perfect phase alignment, well, IIR is going to be your best friend.
Let's dive into section 3, the pole zero method.
Take a look at this graphic. This is a Z-plane unit circle, and it is brilliant for visualizing what's happening mathematically. Here, we are manually mapping poles, which are represented by those little crosses, and zeros, represented by the circles. In the world of digital filter design, zeros literally pull the frequency response down to zero. Think of them like pins tacking a blanket to the floor. They aggressively reject frequencies. Poles, however, push the frequency response up to a peak, almost like a tent pole pushing up the fabric. They allow frequencies to pass through. In this specific visual, we are designing a bandpass filter. Now, a bandpass filter is designed to isolate a specific frequency band while rejecting everything else. It's exactly like trying to isolate a single person's voice in a very crowded, noisy room. To build this, we place zeros at the sides of the circle to reject DC current at 0 Hz and the Nyquist frequency at 250 Hz. Then we place our poles right near the top and bottom edges to force a very narrow passband centered precisely at our target of 125 Hz. It's very visual, very geometric.
So the underlying design logic here really boils down to a simple 3-step process. First, you find your exact Z-plane coordinates based on the real-world frequencies you want to pass and reject. Second, you build out the mathematical transfer function, which we call h of z. And third, you pull out the final numerical coefficients. Those are your specific a and b values, so you can plug them directly into your Python code. It's a very logical progression. Let's actually look at how this translates into the code itself.
All right, let's break down this Python script because this is where the theory becomes reality. Notice how lines 6 through 9 are setting up our physical parameters. We define a 500 Hz sampling frequency and our explicit target rejection frequencies at 0 and 250 Hz. Next, look at lines 11 through 15. Here, we're using some basic trigonometry to translate those physical frequencies into angles, or thetas, on our z-plane to precisely position our zeros. Then, moving down to lines 17 through 24, we execute the exact same trigonometric translation for our poles. We're targeting that 125 Hz passband, and we're using a specific equation to set the radius r to 0.937, which tightly constrains our bandwidth to just 10 Hz. Now, this is the really cool part. Look at lines 28 and 29. By passing our complex pole and zero coordinates into NumPy's poly function, Python automatically expands the roots and generates our numerator coefficients, b, and denominator coefficients, a. No manual algebra required. We then take those b and a arrays and feed them straight into the SciPy signal.frequencies function on line 33 to calculate our frequency response over a range of frequencies. It's super important to understand what comes out of frequency. W returns the frequency array, and H returns the complex frequency response. That H array contains both the magnitude and phase data that we absolutely need to draw our plots.
And here is the visual payoff of all that math. That freq-c calculation we just talked about generated all the underlying data. By using Matplotlib's PLT plot on the absolute value of our H array, we extract the magnitude and generate this top plot. Look at that beautifully sharp, normalized peak right at our 125 Hz target. That is our poles doing their job perfectly. Meanwhile, the curve drops completely to zero at 0 and 250 Hz, exactly as our zeros commanded it to. Then, right below it, by using the np.angle function on that exact same complex H array, we generate our phase response plot. This shows the phase shift associated with an IIR filter across the spectrum. It's tangible, visual proof that our manual mathematical pole zero placements actually work in practice to cleanly isolate a specific band of data.
Let's transition into Section 4, the bilinear transformation technique.
So as we just saw, the pole zero method is very manual and geometric. But what if we need something way more complex? That's where the bilinear transformation technique, or BLT, comes in. This method relies on converting a classic, mathematically perfect continuous analog filter into a discrete digital one. But there's a major catch you have to watch out for. The mapping between the analog frequency domain and the digital frequency domain is not a straight one-to-one line. It's actually warped. Think of it like stretching out a rubber band unevenly. Because of this, step 1 is absolutely vital. We must pre-warp our target digital frequencies before we even design the analog prototype. If we skip this and don't calculate a special pre-warped analog frequency first, by the time we apply the mathematical transformation in step 3, our cutoff frequency will shift and land in completely the wrong spot. Pre-warping is the mathematical trick that guarantees the final digital filter hits our exact desired cutoff frequency. Now, luckily for us, we don't have to do pages and pages of heavy algebra by hand to make this happen. The SciPy Python library makes the actual transformation incredibly easy. Once we have a basic low-pass analog blueprint, SciPy offers these amazingly powerful built-in functions to warp it into whatever type of filter we need. LP to LP for low pass, LP to HP for high pass, LP to BQ for band pass, and LP to BS for band stop. Just to connect this to the real world, a low-pass filter lets low frequencies through and blocks highs, which is fantastic for removing high-pitched static hiss from an audio track. A high-pass filter does the opposite, blocking lows and letting highs through, perfect for removing structural rumble or wind noise from a microphone recording. We just call these functions, and SciPy handles all the mind-bending estimate math entirely behind the scenes. And finally, Section 5. Let's look at more Python code and plots to see the BLT in action. Okay, let's break down another script. Here we are designing a Butterworth filter. Now, Butterworth filters are famous in engineering for having a maximally flat response in their passband, meaning there are absolutely no unwanted bumps or ripples in the frequencies we want to keep. In lines 5 through 9, we set our strict specifications. We want to pass all frequencies below 2 kHz, and we demand at least 20 decibels of attenuation by the time the signal hits 5 kHz to shut out noise. Lines 12 and 13 handle that critical pre-warping math we talked about earlier. Then, line 21 is pure algorithmic magic. The signal.butterworth function calculates the exact minimum filter order n that we need to meet those strict specs without wasting CPU cycles. Finally, the signal.butter function in lines 27 through 34 generates the filter. Here's the kicker. By explicitly setting analog equals false in our code, we are directly telling SciPy to apply the bilinear transformation for us. It automatically pre-warps the data, does the conversion, and spits out our final, ready-to-use digital B and A coefficients. And the plot that comes out of that Python code visually confirms our entire setup. Just look at how incredibly smooth that blue line is in the passband at the top left.
That right there is the signature Butterworth flat passband. No ripples, pure signal integrity. On the graph, you can see the green markers showing our passband edge. Right at exactly 2 kHz, the signal has dropped by precisely 3 decibels, which is standard. Following that curve down to the red marker, our stopband edge, you see it drops to exactly minus 20 decibels right at the 5 kHz mark. It perfectly respects the rules we typed into the script. The SciPy BLD functions effortlessly translated our code into this incredibly smooth, reliable low-pass filter.
But here's a real-world scenario for you. What happens when that gentle, smooth Butterworth curve just isn't aggressive enough? What if you have a powerful noise source, like motor interference, sitting very close to the data signal you want to keep, and you need the filter to just drop off an absolute cliff to save your data?
For a situation like that, we have to level up to a Chebyshev filter, specifically a Type 2 bandstop filter. As we mentioned, a bandstop filter is used to violently reject a specific chunk of frequencies, like completely ripping out a 60 Hz power line hum from a sensitive ECG heart monitor recording. In lines 9 through 13 of this script, we explicitly define our target edges. We want to keep everything outside, but between 1.5 kHz and 2.5 kHz, we want to ruthlessly reject any signal present. Then, lines 16 and 17 do something critical. They normalize these target frequencies against the Nyquist frequency. The Nyquist frequency is exactly half of our 8 kHz sampling rate, so 4 kHz. Normalizing prepares the data perfectly for the SciPy algorithms to process it without errors.
Moving further down the script, we again use an order calculating function, but this time it's signal.cheb2ord to find the absolute minimum complexity required for this aggressive cut. Then, right there in line 44, we call signal.cheb2. The crucial parameter you have to pay attention to here is RS, which we've set to AS. In our code setup, AS is set to 40 decibels. By passing those strict specifications into the Chebyshev function, it mathematically enforces a massive 40 decibel attenuation floor in our stop band, computing those magical B and A coefficients using the BLT method entirely under the hood. And, as you can see in the lower half of the script, we don't just plot the line. We use matplotlib's axHline and fillbetween functions to actually explicitly draw our target boundaries and highlighted zones right onto our final visualization. And wow, look at this brilliant visualization. This plot is drastically different from the gentle slope of the Butterworth. First, notice how incredibly steep that blue line drops off immediately after 1 kHz. It is practically a vertical wall. But the real star of the show here is that pink highlighted zone in the middle. This is known as the equiripple stop band. Instead of a smooth, flat curve in the rejection zone, the magnitude repeatedly bounces off the 40 decibel floor, which is that red dashed line we explicitly programmed Matplotlib to draw. That ripple effect, that is the necessary trade-off in filter design. You sacrifice a perfectly smooth stop band in order to achieve that incredibly sharp, aggressive cut between the exact frequencies you want to keep and the frequencies you're trying to destroy. Ultimately, engineering is entirely about mastering trade-offs, isn't it? Today, you have seen how manual pole zero placement works beautifully for simple targeting tasks. And you've seen how Python's SciPy library uses the bilinear transformation technique to effortlessly generate highly complex Butterworth and Chebyshev filters with just a few lines of code. So, keeping in mind processing efficiency, the need for signal integrity, and exactly how steep of a frequency cut you actually need, which mathematical blueprint are you going to translate into code to clean up the messy, real-world data in your next DSP lab project? Think about it. Thanks for joining this explainer and happy coding.